Ladies and gentlemen, let's continue with Chapter 4, Transient Heat Conduction. The chapter has 4 important parts. The first part is on the lumped system approach. Lumped system approach, very simple equation, and the disadvantage of the method is that you cannot get temperature differences inside the body. And that approach is a good rule of thumb type of approach. Okay, firstly, it is valid for very small bodies, small geometries, and high thermal conductivities. And it is valid when the Biot number is smaller than 0.1. Where did we get that? It is an arbitrary choice. And that choice says the internal resistance is 10 times smaller than the outside resistance, the convection resistance. Now, one of the problems that you have to do in your assignment is, for example, milk. Okay, milk in a container, and there's heating or cooling. I can't remember. If you work out the Biot number, then it is much larger than 0.1. So it would then mean that theoretically you should not use the lump system approach. But what they say is that the milk is stirred all the time. Okay, what does it mean? It means there will be no temperature differences in the inside, so there's no resistance for conduction heat transfer. So for that case, even although the Biot number is larger than 0.1, it would be a valid approach. Okay, right, so that is the one approach. The second approach is to look at very simple bodies that we've considered as one-dimensional heat transfer bodies, and those were plane walls, long cylinders, and spheres. It was the second category. The third category was the semi-infinite solid, a body in which the temperature doesn't change, and we want to see very close to the surface what happens. Again, one-dimensional heat transfer. Paragraph 4.4, the part that we are busy with now, is multidimensional heat transfer. So the heat transfer is not one-dimensional anymore. It can be two-dimensional or three-dimensional. And the building blocks that we've developed, we can apply here and use. Okay. And those building blocks makes it possible for us to use the principle of superposition or the product rule, where we can sort of generate bodies, two-dimensional and three-dimensional bodies, by adding or dividing some of these solutions with each other. Okay, and some of them that has been done is summarized in table 4.5. Now there are many more, okay, but these are some of the simple ones and the ones that we will use in this module. Okay. Now, with a previous lecture, we specifically looked at the short cylinder. Okay, and we have determined the temperature in the center, there at the top and there at that point, after 15 minutes. Okay, and we have seen that we actually can get the temperature distribution. What it obviously also means that the heat transfer wasn't only in the R direction, it was also in the X direction. So it is two-dimensional heat transfer in this case. Okay. Now, the problem that I've just started with the previous lecture is problem 492 in the textbook. And that problem is a block of ice. Okay. The ice at T equals 0 is at minus 18 degrees Celsius, 40 millimeters, and 60 millimeters. And it is standing on a table. And these days, with functions, it's quite an in thing that people will have sculptures on the tables. Okay, so let's suppose this is a sculpture. Okay, and the question is, how long will it take before it starts melting? Okay. The room is 18. Previously, it was the block ice is minus 18 at T equals 0. The room 18, the heat transfer coefficient, thermal conductivity in alpha is given. Okay, so I think that you will all agree with me that that would be one of those corners, would be the point where the ice would start melting most probably. If you're not sure, you can go and calculate it everywhere you want. Okay? But that, in terms of gut feel, that is sort of the logical point where we can expect the ice would start to melt. So the question would now be, let's make use of this method of superposition and the results that we see in the textbook to apply it on this problem. And as indicated yesterday, it is something that you have to be very careful for. Now, after the lecture, there were so many questions about the problem of the symmetry. I'm just going to go through it again before we start solving this problem. And although we are going to solve it, I'm not going to give all the detail. I'm just going to give the framework of the problem, and at home you can just go and fill in all the smaller detail, because it's going to take too long to work through the problem. Okay, so let's just go back to the short cylinder that we've considered. Okay, there's the short cylinder, and the coordinate system, take note, very important, is Rx. That is how the coordinate system looks in table 4.5. So we've used that, and we've used different lines to get the intersects to get the temperature at different positions. Now, the center temperature we have solved as 62.3. Okay, now let's forget the 0.3. Just as a simple problem, I want to show you what I'm trying to indicate here. So let's use 62. And that temperature was not much less, but let's just use 60. Okay, and that one we've solved. It was 40 something, but let's just use 40. Okay, so that we're not going to do so much writing. So that's the only reason. So if we've solved this problem, it is quite simple to understand that that temperature there is also going to be 40, and there also, and there also, and everywhere around the perimeter, the temperature is going to be 40. Okay? And that temperature there, at that point there, is also going to be 60. Okay? So let's move nearer to that point there, and let's do it on a line here. Okay? So as we move nearer, that temperature and that temperature would be the same. Do you agree? And that temperature and that temperature. Okay. Now, let me use 61.9 as an example, because I can't really get closer and closer. But even as I get closer over the line, every temperature on that side is going to be exactly the same as this side. Okay. What does it really mean? Now, except for the fact that we see that the temperatures are the same. It means that the heat transfer rate, if this temperature and that temperature is the same, there's no driving force for the heat transfer in the R direction. You agree? The driving force would be to the outside. So the heat transfer rate would be in that direction. Okay. And from that point, exactly the same, and that point also exactly the same. And at this point here, if you think of a control volume there, control volume, then from this control volume, there will be a certain resistance of heat transfer in that direction, but also in that direction. So some of the heat transfer would be not only in the R direction, but maybe a little bit in the X direction also. And here, exactly the same. And here, on the surface, okay, the heat transfer will be in that direction. So, if we look at it carefully, we can see symmetry along two lines. Okay. The one line would be like that. Okay, do you agree? What does it mean? It would be the same as a problem where that surface is insulated. Okay. So there's an adiabatic surface. Adiabatic means no heat transfer, and partial dt dr or dt dr would be equal to 0. Does it make sense? You happy with that? Okay. And then also along that line, of course. So if we now look at only that half of that cylinder, then again, it would be as if that is insulated. There's no heat transfer in that direction. Again, it is an adiabatic wall, and now partial dt dx would be equal to 0. There's a 0 gradient. And you're using these things in CFD in terms of boundary conditions. And we've used similar type of boundary conditions before in the solution of our equations. Okay. Now, what is important to realize with something like this is if we look at this body, to make it the same as that one, our coordinate system must start at that point there. You agree? Because that doesn't move. And here, it would still be there. Okay? Right. So let's look at the ice. And without now solving the ice, let's just look at the principle first. The principle of the ice is that we've got this block, which is 60 millimeters high, and 40 millimeters width, and then 40 millimeters in that direction also. Okay? And the temperature of the ice is minus 18. Okay? And the temperature here is 18. It's 18 there. It's 18 there, but on this surface, it is not 18. Okay? Okay. So we have a problem with the boundary condition. All the work that we've derived was for a boundary condition where this temperature is the same as that temperature and the heat transfer coefficient all around. Okay. So we've got a boundary condition problem. But again, if you now think of this problem, if it's going to stand on the table, we know that it is going to start melting on the four corners. Okay. The heat transfer is not going to go through the table because they say that, it was in the problem stated, that we can assume that is negligible. So what we have there is actually a symmetry boundary condition. Okay. So we can say, well, let's manipulate that block of ice so that now it is a block of ice which is 60 plus 60 millimeters in length, okay, which means, and that's very, very important, that 2L is now equal to 120 millimeters. Okay. And this line here represents the table. Okay. Of course, there's no heat transfer in that direction. Okay. So if we solve this problem, then that would represent the solution for that. But if we do that, then it is very important that our coordinate system is placed correctly, which would be there. Okay. If you didn't take this symmetry problem into consideration, then most probably you would have put the coordinate system there, okay? And the result is now that 2L is 60 and L is 30. It's going to be wrong. Or you would put the coordinate system there. Okay. So you have to be very, very careful in the position of the coordinate system, and there are many practical problems where you would look at it and you would say, well, one of two possibilities. You would say, but there's no such a solution available, or you would make the mistake of just using the short cylinder to solve the problem without modifying the dimensions so that the problem can be solved. Okay. So what we have in this case now is obviously the block of ice at minus 18, but now our boundary conditions are correct. It's plus 18 all around, as well as the heat transfer coefficient of 12, everywhere all around the body. Okay, you've got it. Right, let's continue and solve the problem. Okay, so what I'm going to do is I'm going to look at the problem in the sense that, and we have to be very, very careful not to confuse ourselves because it can happen very easily. So this is our block again. I'm going to draw it again because there's too much lines and stuff there. Okay. And now our coordinate system is in the center. Okay, it's positioned, take note, that is the Z direction, that is the X direction, and in that is the Y direction. Okay. And I'm going to select this point here as the temperature that we want to determine, that corner there, Tx. Okay. Now to get that temperature, I need to get the solution at 3 different intersections. I need to get it along this line. Let's call that one A. Okay. Then this line, which we call B. And then that line, which is C. And the intersect of the 3 of them will give us the temperature exactly at the corner. You all agree? Okay. Okay, now once you've done it like that, try to keep things simple, and how I did it is as follows, because it can be very, very confusing. Okay. And how I did it is to say, well, let me consider the plane wall, and the coordinate system is now Z and X. Z and X. So I'm looking at it from this angle here. Okay, Z and X. It would mean that that would be 2L, and 2L will be 40. Okay, 2L is 40. It's the width of the ice. And what we have to be careful for is that we now have 3 L's. Okay. And you're going to see later on 3 Biot numbers, 3 lambdas, etc. So you have to be very, very careful in your handling of it. So what I'm going to do is I'm going to call this L1. Okay, let's call it the first part of the problem. So this is 2L1, which is 40. Right. Now for this problem, we need to calculate the Biot number, which is equal to the heat transfer coefficient multiplied by L1 divided by K. I'm not going to fill in everything because it's elementary. Let's go through it quickly. The heat transfer coefficient is 12. Okay. L1 is now 20 millimeters. Okay, you agree? L1 is 20 and the thermal conductivity is 2.22. So if you calculate the Biot number, then it is equal to 0.1801. If you have the Biot number, you can get the roots from the equation of the plane wall, or you can get it from table 4.5. I'm not going to waste time with that. I'm just going to give you the answer. And it is, lambda is equal to 0.3208, and A1 is equal to 1.073. Again, I'm going to assume that tau is larger than 0.2. Why? So that I only have to do the first solution of the non-dimensionalized temperature equation. Now, let's look at the second one. Oh, sorry, I forgot. What is important is that we have to solve now the temperature along that line. Okay, so that would be where X is equal to 20 millimeters. Okay. So we need to get the solution where X is equal to 20 millimeters. Let's look at the other one. And the other wall is now the ZY direction. okay, zy. So that would be this side here. Okay, this side here, which is also 40 millimeters wide. Okay. So again, that distance is equal to 2L, but because I've got an L and an L and an L, I'm going to give it the nomenclature of L2. Okay, it's 40 millimeters. And now we need the solution along that line there, B. Okay. And obviously you can do it the other way around also. You can go to that side. At the end you must just get to one of the corners. Okay. Now, the calculation of the Biot number is equal to, again, the heat transfer coefficient, but now L2 divided by K. In this case, L2 is also 20 millimeters. So it's the same as with the previous one. So if we calculate it, it is equal to 0.1801. Okay. And now, when we go and get lambda 1, then it is equal to 0.3208, and A1 is equal to 1.0173. Yep.
Is your coordinate system in the middle of the ice block, or is it on the right-hand face?
No, it's in, it is difficult to say, but it's in the middle of the ice block. Yep, it's in the middle, yeah. Okay. Did I draw it somewhere wrong?
So shouldn't that line BB, shouldn't it be AA?
Okay, so this one is AA, okay. Okay. And this one is then?
I think what you're supposed to do is to the horizontal line where Z is equal to 20.
Okay. Now I'm getting to that one just now. Okay, let me make my drawing a little bit different. Yeah, okay. Make it different. No, there are two of them. There are two of them from the side. Okay, there are two of them off the side. Okay, let me just do the third one quickly, and then you'll see it is easier. Okay, so the third one would be the top one. Okay, the top line. Yeah, okay. Okay, and that one would be Z and Y. Okay, and then we will solve the C line there. Okay. So with this one, we should also get it like that. Y and Z. It's the same as that one. So this one should be X. Okay. We're all confused now. Okay. Okay, wait. For this plane, we need to go to there. For that one, we need to go up. YZ. Okay, wait, YZ. And that. YZ. C. X, Y, Z. Okay. That's right? Okay. Get yourself confused very quickly, as you can see. Okay? Okay. Okay, and then this would be the B line. Is that right? Something like that. Okay, so let's look at it from this angle. Let's look at it from this side. Okay, if we look at it from this side, we will see X to the right and Z to the top. Do you agree? and we need to get the line A to get to that point. You agree? Okay. Then the next one is, let's look at ZY. So we look from here. Okay, you see? Now Z is up, Y is there. So that would be that C line there. Okay. Okay. And then the third one is we're going to move to look at it from the ZX direction. Okay, ZX. That must be ZY. No. But we've looked at it that we have to look at it from ZX. Yeah, ZX. ZX. No, ZX from the top. Okay, let's. I've already done ZY. What? YX. Yes. YX. Okay, YX. Yeah, okay. Let's go through it again. Just a minute. I'm going to explain it and so that I can also get out of my own confusion. And let's see if we can get it. Okay, so we look at it from this angle, and then we see X and Z. X and Z, and we need to get to that line there. You all agree? Yeah. All right. Then we need to look at it from this angle here. Okay, or from the X. Okay. We see X, we look from X, and we see Y and Z. Y and Z, and then we have to look at that line there, C, the C line, okay? Okay, then the last one is YX, so we look at from the top, okay? YX. Sorry, I can hear somebody speaking, I cannot hear.
You can't look at it from the top because you don't have any points of reference there, like any TI.
Why can't I look at it from the top? Because if I look from the top, it is Z, and then I see that. Okay. And then I've got X there, and I've got Z there, and then I need to get that line there. If you look at it from the top, then
the Biot numbers will be the same, all of them.
Yeah, but forget about the Biot numbers now. Forget about the Biot numbers. No, they're not going to be the same. I'm going to show to you that that's not the case. Okay. Some of them are going to be the same, but not all of them. Yep.
Why does it really matter if we consider different lines to look at the different angles?
I'm going to explain to you just now. Okay. Yep.
So wouldn't it be easier if you just did the flow of energy in the X and the Y and the Z direction?
If I do what in the X and the Y and the Z? The what?
The flow of energy.
The flow of energy.
The flow of energy in the X direction, in the Z direction.
Yeah.
Energy in the Y direction.
Okay. Okay. They are okay. We are not going to try to get more solutions to solve the problem. Okay. So we can look at that later because we're going to run out of time. Okay. Just the last one.
How do you know from what perspective you look at what line you're busy calculating? You can't look at in the X, Z plane. You can calculate line B as well. So
you can use different ones. So there are many options. Ladies and gentlemen, let me just finish the problem, and then we can look at some of the details. Okay. Okay. So just be a little bit patient with me. Okay. So in this case with ZY, let me just see. If I look from, okay, then that distance is now going to be 120. Do you agree? Okay. So this Biot number is L2, and L2 is 60 millimeters. Okay. Okay, now this one, if we look at it from the top, then that distance is going to be, 2L is going to be 40, or L, 2L is 40, and therefore L3 is 20. Okay. So, if I now just look at the Biot numbers, then this Biot number, if I use that, would be equal to 0.3243. Okay. This one is the heat transfer coefficient multiplied by L3 divided by K, and this L and that L is the same, so it would be equal to 0.1801. So do you see that all the Biot numbers are not the same? Because the dimensions are not the same. Right, because this can be so confusing, let's number them. And we are going to number them as the first Biot number, the second Biot number, and the third Biot number. Okay? This is going to be lambda 1 of the first equation. This is going to be A1 of the first equation, and that would be tau 1 of the first equation. Okay. This is our second case. Okay. So this is our second Biot number, that's our second lambda, and that is our second constant A1. Okay. The second A1 constant. Okay, not A2. Okay. And again, we are going to assume that tau 2 is larger than 0.2. Okay. Now with this one, lambda is, sorry, I've made a mistake here. Let me just correct that. So that would be 0.5392 and 1.0482. Okay, and that would be the same, 0.3208, and A1, which would be equal to 1.073, and this is the third A1. And the tau would be the third one, again making the assumption of 0.2. Okay. Right, now if we look at tau, okay, now tau is equal to alpha t divided by L1 squared. Okay. This tau is equal to alpha t again, but now L2 squared. And this one would be equal to alpha t divided by L3 squared. So you can see that in many cases when we have to solve tau, and we did solve tau, that it wouldn't be valid for all three equations, because we might have three different L's. Now in this case, this one and this one are the same. So this tau and that tau is the same, but let's call that one 2, and that one 3. The only thing that is, well, not the only thing, alpha is obviously a constant, but the t, there's no T1, T2, and T3, but there's tau 1, tau 2, and tau 3. They might have different meanings. Okay. So in general, we can say tau 1 is not always equal to tau 2, is not always equal to tau 3. For this specific problem, yes, tau 1 is equal to tau 3 because the L's are the same. But if you would like to call this T1 and T2 and T3, then T would be equal to T1 is equal to T2 is equal to T3. Okay. How's the solution going to look now if we want to solve it? Okay, so the solution of a body like that is in general equal to the solution of a plane wall in the xt direction, the solution of a plane wall in the yt direction, and the solution of a plane wall in the zt direction. So the non-dimensionalized solution at the intersect between the lines A, B, and C, okay, would be the solution where x is equal to L1, where y is equal to L2, and z is equal to L3. And the unknown is the temperature that we need to solve. And that would be the solution of the plane wall in the direction L, for the thickness L1, for the thickness L2, and for the thickness L3. Okay. Now, as I've said, I'm not going to give you everything in detail. You'll have to go and put in the flesh for this problem. But the problem is now going to look like this once you've done it. It is going to be the temperature at point X. That is the temperature that we want to solve. Okay. Minus T infinite divided by Ti minus T infinite, okay, is then going to be equal to, okay, A1 E to the minus lambda 1 multiplied by tau 1 multiplied by the cos of lambda 1 multiplied by x divided by L1. That would be the first term. Now, you're going to have an A1 here and an A1 and an A1. And that is why I've indicated them that let's call this A1 of the first equation, A1 of the second equation, and A1 of the third equation. So that should be for the first equation. It's the lambda of the first equation. It is the tau of the first equation. The lambda of the first equation. Okay? You agree? That is how it's going to be as the first term. So the second term, again, A1 e to the minus lambda 1 multiplied by tau multiplied by the cos of lambda 1 multiplied by x divided by L2. Okay. Now it is the second A, it is the second lambda, and that would be the second tau. Okay. Multiplied by the third one. The third one would be A1e to the minus lambda tau multiplied by cos lambda x divided by L. Okay. But now it is the third value of the A. It would be the third lambda, the third tau, and again the third lambda. And that is our equation. Okay? Okay. Now look at it carefully. We've got A1. Okay? A1 and lambda 1 we have. Okay. So we can put it in there, we can put it in there, there, and there. Our only unknown is tau 1. You agree? Okay. Here the same. That constant is known. The lambdas are known. The unknown is tau 2. Again, constant known, everything known except tau 3. So this equation now becomes the temperature at X is 0. We want to know how long does it take before the temperature gets to 0. Minus the temperature on the outside, the ambient temperature, which is 18, divided by the initial temperature of the block of ice, was minus 18. Minus 18, again, is then equal to lots of constants and terms multiplied by tau 1. Okay. Plus lots of stuff, and there should be a tau 2, plus lots of stuff and a tau 3. Okay? These values are obviously equal to alpha t divided by L1. This one should be alpha t divided by L2, and this one should be alpha t divided by L3. The only unknown is the temperature. Okay. We want to know how long it is going to be before the temperature reaches 0. The alphas are known, and we've got the L's. Do you agree about the principle? Yes. Right. So, not easy to solve, as you can imagine. Maybe you'll have to do it iteratively, or you can use ease. And if you do that, then the time is, who would like to guess? How many hours before the temperature would get to 0? You say 4? 29? 6 hours? Okay. The time is 70,020 seconds. To an engineer, that doesn't mean anything. That means it is 19.5 hours, almost 20 hours before it would start melting. Okay. Ladies and gentlemen, do you agree in terms of the principle of the problem? If you can quiet down there, there's a question there, and I would like to hear what the question is.
The terms in the non-dimensional temperature.
Yep.
There was a lambda x on L2. Isn't it supposed to be lambda y on L2?
Sure. Okay. Sorry. Yeah. You can. That should be x, y, and z. Yeah. Okay. X, y, and z. Sure. Okay. If you would like to keep to a consistent nomenclature. Any other questions, ladies and gentlemen? Okay. Okay. So as you can see, when you start these problems, even although I did it before the time and draw out my lines, you can confuse yourself very, very quickly, very, very easily.
Just
question?
Perspective on your third drawing there, the one to the most right.
Yeah.
That B line, shouldn't that B line be at the bottom?
Okay, he wants the B line at the bottom. Put it at the bottom. It's going to change nothing in terms of the calculations of everything. Do you see? So you can also put it at the bottom if you want it at the bottom. Again, remember, if you put it at the bottom, if you want it here, then the L is still going to be 20 millimeters. So everything would still be the same. Okay. Ladies and gentlemen, yeah, you have to quiet down. We still have to do a few more things. Okay. Any more questions on the work? Okay. So this ends chapter 4. Thank you very much. And Aaron, you can cut. Okay.